All right, here comes the review for the final. The final is comprehensive, but this video is only going to cover the second half of the course. Let's start with polynomial functions. Here's a third degree polynomial function. We want to find the possible rational zeros by the rational zeros theorem. We have these. How do you find the actual zeros though? Well, if you have the graph in front of you, you can look at the x-intercepts to find the real zeros, right? Or you could use the table feature. It looks like we have a real zero at -1. We have an x-intercept at -1, 1 and 1/2. So you could write it, which are the all rational zeros, you could write it as x plus 1, x minus 1. And instead of saying x minus 1/2, since the coefficient has to be 2, you could also say 2x minus 1. That's a better choice, isn't it? And the end behavior, you can see. Let's look at another one. This one is a third degree polynomial function. If you look at the possible rational zeros, you get this. Again, let's look at the graph here, or the table feature. It looks like a x-intercept at 2, so x minus 2 is a factor. These other two x-intercepts, I don't think they're these, so they must be irrational. They're real zeros because they're x-intercepts, but they're not rational ones, so there must be irrational, it looks like. How do you find them? When you divide x minus 2 into the polynomial function, it goes in evenly, and you have this. So you could actually factor a negative out of that. So this is where we are so far. And then to use the quadratic formula on this, you get two irrational zeros. So how would you finish this problem? You'd write it in factored form like this. On this one, third degree polynomial function, these are the possible rational zeros. You could use a table feature or the graph. Look, there's only one x-intercept. How could that possibly be that you have a third degree polynomial function with one x-intercept? That means the other two zeros, remember every polynomial function of degree 3 has exactly 3 zeros. The other two have to be non-real. So how do you find them? Well, you could divide the polynomial function by x minus 1. It goes into evenly, and this is your quotient. Then when you try to set this equal to 0, boom, you get two non-real zeros. So this is how you would factor it into, these are all the zeros, one real, two non-real. This is how you'd factor it into linear factors. Okay, let's keep on going. What if you're given a graph and you wanted to find the equation? Well, one of the things you could do is look at where the x-intercepts are. See how this turns here? Remember what happens if it turns? That means you have an even multiplicity. It looks like a third degree polynomial function. So perhaps it would be x squared here instead of x. This looks like 9/2. So let's say x minus 9/2. And then to find a, you don't assume a is 1. A is a constant. You could pick a point like 1, -1 looks like a point on the graph. When you plug 1 in here, you get 1. When you plug 1 in here, you get -7/2, right? Anyway, so if you solve this for a, you get a is 2/7. So this would be the answer. Try this one on your own. See if you can do this one. Hit the pause button. Let's keep going. This one looks like a fifth degree polynomial. I know it's odd degree, and I know it has 1, 2, 3, 4 turning points, so it's probably a degree 5. It has zeros at -2, -1, 0, 1, and 2. I don't know what a is, and frankly, I don't even know how to read from this graph, so I'm not going to even try. I do know that a is negative because of the end behavior. Why don't you try this one? Hit the pause button. Okay, let's keep going. So another thing you could be asked to do is I would give you information about the polynomial function, and you have to come up with the equation. That's kind of fun. It has degree 3, 0 at -2, so x plus 2 is a factor. 1, so x minus 1 is a factor, and 3, so x minus 3 is a factor. P of 0 is 5, so you can plug in the point 0, 5, and I get that a is 5, 6. You can check me on that. Okay, try these next two. Try B and C to get these answers here. Okay, let's do rational functions now. Rational function is very different than a polynomial function. What's different about it? You can have vertical and horizontal asymptotes, and so it's the end behavior also that's different. Anyway, so you have an x-intercept where the top is 0. To find the y-intercept, all you have to do is let 0 equal x. You get 3/4. Vertical asymptote is where the bottom is 0. And then to find the horizontal asymptote, if the top and bottom have the same degree, it's the ratio of the leading coefficients, so it's -2. This one, we factor it. I would suggest factoring a -1 out if you're going to try to find the places where it's 0. So you get down to this. X-intercept, be careful. There's not an x-intercept at -1. In fact, there's a hole there because they can't cancel. There's a hole at x equal -1. The only x-intercept is 3. And the y-intercept, go back to here, plug in 0 for x, you get 3 halves. Vertical asymptote's where the bottom is 0. This is not a vertical asymptote. Remember, it's a hole there. X equals -2. Now, how do you find the hole? Well, you know x is -1, right? But how do you find the y-coordinate? How do you know it's 4? It looks like it might be 4, but if you just cancel that factor there and you look at what's left, you can actually see that if you plug in -1 here, you get -4 over 1, but there's a negative of that, so you get 4. So that's how you can find the y-coordinate. Last one I'll have you look at, but let me just mention this. This one does not have a horizontal asymptote. It has what's called a slant asymptote because the top has 1 degree more than the bottom. So how do you find the slant asymptote? You can tell there's a linear function here, a linear asymptote, same as a slant asymptote. You use long division. You divide the polynomial by, you divide this polynomial by x minus 3. The quotient is x plus 7. So that would be the slant asymptote. Okay, on these, you could be given a graph of a rational function. This looks like a x-intercept at 3, so x minus 3 is a factor. Looks like a vertical asymptote at 2, so x minus 2 is a factor. And since the horizontal asymptote is 2, you have to have a 2 in front. If you didn't have a 2 in front, wouldn't the horizontal asymptote be 1? So to make it 2, you do this. All right, I'll let you guys finish these two on your own. Hit the pause button. Let's look at this. Find a rational function that satisfies the following condition. It has an x-intercept at -2, so you know x plus 2 is a factor on the top. Vertical asymptote at 1, so you know that x minus 1 is a factor at the bottom. Horizontal asymptotes at -3, that means the top and bottom have the same degree. Right now, if you didn't have that -3 on the front, on the top, wouldn't the horizontal asymptote be 1? So to make it a -3, you put a factor of -3. That makes the ratio of the coefficients -3, and it doesn't mess up the x-intercept of vertical asymptote. Okay, I'm going to have you guys try these. Try B and C on your own. Okay, let's move on. Now, the last section in chapter 3 on solving polynomial and rational inequalities, you pretty much solve them the same way. You want to get 0 on one side, and you want to factor, right? I'll do this one. You can try the other two on your own. So let's look at this one, rational inequality. You factor everything, and you plot all the places, all the x values where either the numerator or denominator is 0, and you plot the factors here. And then what you do is you have to test and see what is the sign of each of these factors in each of these regions. So for x minus 5, it's going to be negative, 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 until you get past 5, then it's positive. So you do that for each of them. You determine the sign of each factor in between each of the values, each of the zeros. Now, when is a product or quotient of 4 things negative? Well, you have to have an odd number of negatives, right? So this region would work, and so would this one. However, we're not going to include -3, even though it says or equal to 0, because at -3, the bottom is 0, so it's undefined there, so you don't include that. But you do include it at -2, because having a 0 on the top is fine. It makes it 0. Also, in this region, we don't include 3 because, again, it makes the bottom 0, and we do include 5. So this is the solution. Now, I'll let you folks try number 11 and try number 12.